Okay, we will start the session. Today, we are going to see the cone clutch analysis. Okay. Today's topic is cone clutch. We are going to see the torque analysis and then corresponding cross-section design for the cone clutch. Now, let's understand when and why we use cone clutch. We have learned single plate clutch as well as multi-plate clutch. Now, the maintenance of or manufacturing of single plate or multi-plate clutch is quite difficult and quite costly also. So many times you need to transmit power and you need the quick engagement, easy operation, and the cost of the components should be minimum. So in such cases, if you have light work, light load to be transmitted, then cone clutch is effective mechanism to transmit power from driver shaft to driven shaft. So one such diagram is shown here. So this is a driving shaft, which is the one end of the driving shaft. We have mounted a cup, okay, a conical cup, and the other shaft, driven shaft, uh, which has a spline end. On that spline end, we have mounted a cone. So this is a cone, and this is the cone hub. Then this cone will be moved forward or backward with the help of spring force and actuating lever. So this spring force will keep this engaged, and actuating lever will disengage this cone with respect to this cup. So between this cone and cup, either on the cone surface or on the cup surface, a friction lining can be mounted. So mostly friction lining is mounted on the cone surface. Uh, Sometimes it can be mounted on the cup surface also. Now this cone will be having angle. So this angle is called alpha, or that is called as a semi-cone angle of the uh, cone. So this angle helps you to facilitate the engagement properly. This cone angle, semi-cone angle, alpha, easily a small displacement moment will create a gap here, and this gap will disengage this driving shaft and driven shaft. Okay, so engagement and disengagement is very quite easy in case of cone clutch compared to the plate clutches and multi-plate clutches. So for a better understanding, you can see the 3D diagram. Okay, so and the components of your cone clutch. So cone clutch, I have shown this diagram again, and the simplification and understanding purpose, you can see the 3D diagram. So this is a cup. This is the driver shaft on which this at the end of the driver shaft, this cup is mounted. This cup has internal taper. So internal conical surface is there on this cup. Then the this is the driven shaft on which we have a spline end here. On that spline end, uh, cone with hub is mounted. Okay, and this cone can move forward or backward under the action of forward motion will be under the action of spring, and backward motion will be under the action of actuating lever here. Okay, so you can engage and disengage this cone properly. So you can see the components, main components of this cone clutch. That is a female cone, which is shown in green color here. This is the female cone, or this is the that is called as cup. And then there is a male cone, that is a basic element of your cone clutch, on which the friction material is mounted. You can see here is the friction lining mounted on the cone. Shafts are there. So this is the driven shaft, flying shaft, on which this hub can move. Then there is a spring. Spring. Mostly we have seen in the single plate clutch or multi-plate clutch, number of springs are used. But most in case of cone clutch, only single spring will be used, and that single spring will be mounted coaxially with the shaft. So normally single spring will be used of appropriate stiffness. Then we have clutch mechanism or lever mechanism, and how to rotate it so that the rotational diagrams, when it is rotating like this, so it will rotate also in the same direction. So this is the construction and working of your cone flux. Now let's go to the analysis. Okay. So to analyze this cone flux, we are taking a small conical element here. So this is the conical element having inside diameter say D or outside diameter capital D. Or you can change it, say this is say D2 and this is D1. Axial force P or W here. So here it is written P, but in design calculation I will use as W. The semi-cone angle here is alpha, and you can consider pressure intensity at any location here. So at this location, say the pressure intensity is P. Now this element, we have taken a radial element, a small element having at a distance R here. So you have taken this inclined length. So that inclined length, you can say this is the inclined length, having radius at this end R, and at this end the radius is equal to R plus dr. So this distance will be equal to radial distance will be equal to dr. So the length of this contact surface here, this length of this contact surface, since this angle is semicone angle is alpha, so length of this contact surface is dr upon sin alpha. Okay. So on this surface, various forces will be acting. So this is that surface we have shown here. So on this surface here, normal force will act. So that normal force will be directly proportional to the pressure intensity P and the area at that location. So that area at that location, you can say D or delta A. So the total force acting on that small elemental ring will be equal to this pressure intensity into this area. So again, this area is not a plane area. It is a lateral surface area, conical surface area. So you need to consider that conical surface area. Then these force components, normal force component can be divided in two components. That is, one is axial component and one is radial component. So axial component will be P d delta A sin alpha. So this P delta A is the value here. So you can take this axial component in terms of it is opposite side of angle alpha here. So it will be sin alpha. And this is the radial component of the force acting at that point. So that will be P delta A cos alpha. Okay. So the small element, Itna element, we are expanding here, then showing the pressure intensity and the force calculation. Okay, so for better understanding, now come to the considerations here. So we are considering it's a single cone, not plate, it's a cone flux with following specification. So we have W here, that is say this P is replaced by W here. So W here is total axial load required. So that this cone can be kept engaged with cup. Then R1 is the external radius of cone flux. So this value is R1, that is equal to then R2 internal radius of cone flux. So this is the end internal radius of the cone flux. P intensity of pressure between contact surface. So P value here, this P value shown here is the intensity of the pressure on the contact surface. Mu is the coefficient of friction between contact surface here. Here, whatever the mu coefficient of value here, friction value that you are considered here. And alpha here is semicone angle of the flux. This alpha here is semicone angle of the flux. Now considering elemental ring. So let's say consider elemental ring of radius r and thickness dr. So radial thickness dr we have considered here. Then area of the ring on contacting surface. So area of that ring on the contact surface dA will be equal to it is an perimeteral area. So perimeter is equal to 2 pi r, and the width of that area width is the lateral width. So lateral width is here dr by sin alpha. So lateral width is equal to dr by sin alpha. So this will become a developed rectangular area having perimeter 2 pi r, and width of that perimeter rectangle is dr upon sin alpha. So this is the contacting area for elemental ring. So normal force acting on this elemental ring. Is this normal force acting on this elemental ring here? I am writing it with a small force dP will be equal to pressure into area of the ring. So pressure intensity is equal to P. Area of the ring is dA, that this value. So 2 pi r into dr by sin alpha. So when you put this value here, so we get 2 pi P into r into dr by sin alpha. That is the elemental force, normal force acting on this surface here. This surface here. At this What is the force acting? Very small surface here. Now, this force, since this is a normal force, there will be associated frictional force. So frictional resistance offered by the ring, we are considering dFr. So which will be equal to normal force into the coefficient of friction. So this is the coefficient of friction, and this is the normal force. So by putting the value of normal force, frictional force comes out to be 2 pi mu into P into R into dr by sin alpha. Now, whenever there is a frictional force, and since the components are rotating, so there will be frictional torque associated. So frictional torque, now this is for elemental ring. So frictional torque for elemental ring will be dmt, that is equal to radius into the force acting there. That force is equal to dfr. So if you put this value here in this equation, so you get this torque acting on that elemental ring is equal to frictional torque is equal to 2 pi mu pr square into dr by sin alpha. Therefore, if you want to calculate the total capacity of this cone clutch, then total torque transmitted by the cone clutch here, you can say this is plate surface which is bent in the conical form. So that is equal to mt is equal to integration from R2, that is say this is R2 to say this is R2 here to R1 here, maximum radius here, dmt. So again in this equation, when you are putting the mt value here, constants can be taken out. So 2 pi mu is constant, and alpha for given geometry of the cone, alpha is constant. Hello? 2 pi mu upon sin alpha being constant, we are taking outside the integration. So what is left out in the integration is P into R square into dr. Since we don't know how the P is going to vary or whether remaining constant, so this will remain in the integration only. Then elemental axial force. So we require to engage this cone with the cone cup surface. So you required axial force here. So the elemental axial force I am writing as dW, which will be now from this diagram here, that dW will be in the axial direction. So this is a separating force. So spring has to provide exactly equal and opposite to this force, and that is equal to P into delta A sin alpha. So that will be equal to dP into sin alpha, that is 2 pi P into R into dr by sin alpha into sin alpha. So sin alpha will get cancelled out. So elemental axial force will be equal to 2 pi P into R into dr. So this is an elemental axial force for small element of ring here. Now if we consider the entire width of the cone, then total axial force will be integration from R2 to R1, 2 pi being constant outside, R2 to R1 integration, P into R into dr. So that will be the total axial force required for this cone clutch engagement. So this force will be developed by spring, and this will be always acting so that we can have engagement. So P is the pressure intensity and R is the radius. So this being radius varying from R2 to R1, so we can evaluate total force requirement. So this is a general cone clutch analysis. Now you cannot directly evaluate this W value and MT value. You need to use proper theory to evaluate the torque value and the axial force value. So this can be done with say assuming uniform pressure theory. So first let's take the case of uniform pressure theory. So what we are assuming here, we have this diameter, say small end diameter of the cone as D2 diameter with radius R2, and big end of the cone diameter is cone is equal to D1 diameter with radius R1, and we are assuming here on this surface, a conical surface here, the pressure intensity developed is equal to P, and which is constant. So everywhere the pressure intensity at any radius here is equal to constant. So that's why we are assuming this theory as uniform pressure theory. Okay, so considering uniform pressure theory, let's evaluate how much torque we can transmit with a cone clutch and how much engagement force will be required here. So assuming uniform pressure theory, we have P is equal to constant here, that is pressure is equal to constant. So total axial force required, this formula we are taking from the previous slide, that was equal to 2 pi PR dr. So 2 pi. Now since P is equal to constant in this case, so this P also can be taken outside the integration. So we get 2 pi p into R2 to R1 RdR. So integration of this will be R square by 2. So 2 will get cancelled out here. And if you put the limits, then this will be R1 square minus R2 square. So we get W is equal to pi p into R1 square minus R2 square. So this is the W in terms of radius value. But normally it is specified diameter. So W in terms of diameter will be here pi p by 4 into d1 square minus d2 square. Now this is the total axial load when you consider uniform pressure theory. This is the total axial force to be developed by spring so that the cone clutch is always in the engagement. So the pressure intensity for given axial force. So if W is known to you, so you can calculate pressure intensity at that surface. So you can rewrite this formula. So P is equal to, in terms of radius, W upon pi R1 square minus R2, or you can write in terms of diameter, then pressure intensity is equal to 4W upon pi into D1 square minus D2 square. So this is the formula for uniform pressure theory, pressure intensity evaluation, considering uniform pressure. Now, this is the requirement of axial force as well as average pressure value. Now, let's go to the total torque transmitted. So, will be integration from R2 to R1, dmt. This value will be written from the previous slide, and the constants are taken outside. Since P is constant, that is also taken outside. So, we have 2 pi P mu upon sin alpha, integration R2 to R1, R square by D. So, integration of R square will be R cube by 3. So, finally, you get answer by putting upper limit and lower limit here. The torque transmitted here is 2 pi p mu upon 3 sin alpha R1 cube minus R2 cube. This is the value of torque transmitted considering uniform pressure theory. So, in this formula, you can replace this formula by instead of radius term, you can use diameter term. Then, if you put this diameter term there, so d by 2, so 2 raised to 3, that will come as 1 by 8. So 1 by 8 into 2 upon 3, that will come as pi by 12, means 1 by 12. So by putting the diameter in the form of diameter, this formula is pi p mu upon 12 sin alpha into d1 cube minus d2 cube. Okay, so this is the formula in terms of pressure intensity and the diameter of cone, inside diameter and outside diameter. That is small end diameter and big end diameter. Suppose if you don't know the pressure intensity, but if you know the W value, so then how to calculate MT? So you can replace this P value by this formula. So you can put this P in terms of this or P in terms of this. So if I put if I take first case, then MT is equal to 2 by 3 pi mu. This formula I am using here upon sin alpha. So we are putting the value of P in this equation. So P is equal to here W upon pi R1 square minus R2 square. So W upon pi into R1 square minus R2 square. Then this is as it is R1 cube minus R2 cube. So this pi will get cancelled out. Then whatever left out is, say, MT is equal to 2 mu into W upon 3 sin alpha. And here R1 cube minus R2 cube upon R1 square minus R2 square. So this is the formula in terms of radius. But many times we use the formula in diameter form. So diameter formula here by replacing R1 and R2 by D1 by 2 and D2 by 2 respectively. So MT is equal to mu W upon 3 sin alpha into D1 cube minus D2 cube upon D1 square minus D2 square. So this is the torque transmitting capacity considering uniform pressure. Okay, so I think you may have understood to this level. So let's go to the next theory, that is uniform wear theory. So this theory is used only when your cone clutch is new, and if your cone clutch surface is wears out, then you have to go for uniform wear theory. So uniform wear theory. So in cone clutch analysis, considering uniform wear theory. So you can see there is an axial force W here. This radius is R1. This radius is R2 here. And on this surface here, contact surface here, the pressure is acting. Now, right now, the pressure is not constant. Pressure is varying as we change the R. And for minimum radius, the pressure intensity is maximum. And maximum radius, the pressure intensity is minimum here. So, on the contact surface, this pressure variation, the bearing pressure is changing here, or clutching pressure is changing. So we are considering the maximum value at the inside side, and based on that, we can design for uniform wear theory. So we are assuming here linear variation of the pressure. That is, we are considering P into R is equal to constant here. That is, if we change the radius, so intensity will change. If we increase the radius, intensity will decrease. If we decrease radius, then intensity of pressure will increase. So we can write down P into R is equal to constant, means P1 R1 is equal to P2 R2. Then we can write down dW, elemental ring consider करके P into dA, that is equal to 2 pi P in PR dr. Since P into R is equal to constant here, so this can be replaced as P1 R1 or P2 R2. So I am replacing with P2 R2. So when we put in this equation, this can be taken outside because this is a constant value. P into R product is constant. So we are taking that P into R outside in terms of known value of P2 R2. So P2 R2 is taken outside. So what is left out integration is only dr integration. So integration of dr is R1 minus R2. So we get this value as 2 pi P2 into R2 into R1 minus R2. This is in the radius form. We can convert into the diameter form. So pi into P2 into D2 by 2. 2 will get cancelled out. So upon this D1 by 2 minus D2 by 2. So that 1 by 2 will be common outside here. So D1 minus D2 here. So this is the formula for axial force to be supplied by spring in terms of diameter. Okay. So this P2 is nothing but I am considering here is the maximum pressure. That is the at this point. This is the radius R2. So this is the P2 value. So P2 value is equal to P max is equal to W upon 2 pi R2 into R1 minus R2, or 2W upon pi D2 into D1 minus D2 in terms of diameter, and this formula is in terms of radius. Please remember, there is no data available, no diagram available of the cone clutch in PhD. So you have to remember most of the formulas for cone clutch. Whenever there is a problem asked in the cone clutch, then you have to remember these formulas, or you have to make a trick to remember this formula. Okay. So this is the pressure intensity or maximum pressure intensity for uniform wear theory. Then torque transmitted considering uniform wear theory. So DMT. So we are taking constant outside 2 pi mu upon sin alpha into R1 R2 to R1 P R square into dr. So P R square can be divided in two parts. That is, one part is PR and another part is R. So PR into R. In that, P into R is equal to constant. So 1 P into R is equal to 1 R is equal to constant. So which can be taken outside in terms of value of P2 R2. So we are taking that P into R outside. So whatever left out is only RDR here. So integration of RDR is R square by 2. So R square by 2, 2 will get cancelled out. So the integration comes out to be here pi mu P2 R2 upon sin alpha into bracket R1 square minus R2 square. Now in this equation also we can put the value of P2, that is equal to P max. So value of P2, that is equal to P max in terms of radius, this value is there. So this value can be put here. So after putting that value, you get the torque transmitted in terms of radius is equal to mu W upon 2 sin alpha into R1 plus R2. This formula can be converted into diameter form, that is equal to mu W upon 4 sin alpha into D1 plus D. Now this is the torque transmitted considering uniform wear theory. So this formula is different, and if we go to the previous slide, this formula is different. So this formula is based on uniform pressure theory, and this formula is based on uniform wear theory. Okay. So if you see in the single plate clutch, the formula for single plate clutch was mu W upon 4 into D1 plus D2. Now formula for cone clutch is now mu W upon 4 upon sin alpha upon D1 upon D2. So if you take the ratio of the torque transmitted by cone clutch and the torque transmitted by the say single plate clutch for same geometry, that is same diameters D1 and D2, then the torque transmitted by cone clutch is greater than the torque transmitted by single plate clutch. So how much it is greater? So it is greater by 1 upon sin alpha. If that so that 1 upon sin alpha, and sin alpha will be always less than 1. So if alpha is equal to greater than say greater than 0 but less than say 90 degree, then alpha sin alpha value will be less than 1. So 1 upon sin alpha will be greater than 1. So torque transmitted by cone clutch will be greater than a single plate clutch of same geometry. That's why in many applications, the cone clutch being used instead of single plate clutch. Because the torque carrying capacity of single cone clutch of having same diameter ratio is greater than single plate clutch. Okay, then this is the inclined width of the contact surface. So many times you require this inclined width in the calculation. So how to calculate this inclined width of the say contact surface or the contact surface width? So face width of the friction lining is given by B is equal to, this is D1 and this is D2. So D1 minus D2 upon 2 sin alpha. Now let's talk about alpha here. Alpha is the semicone angle, and there is a need, then this alpha angle need to be again standard. So how much angle you should consider? If we consider this angle very small, then B will be very large for given geometry. But the advantage of this alpha being small here, suppose if we see here this formula for MT, if this alpha is small, so 1 upon sin alpha value will be greater. So that cone clutch can transmit maximum torque. So it can transmit maximum power. So to transmit maximum power, you have to keep this angle alpha small. But if you keep this alpha very small, then there is a problem. Under the action of centrifugal action only, there is a possibility of self-engagement of the clutch. There is a possibility of self-engagement. So this angle alpha has to be sufficiently large, not very small. It should be sufficiently large such that the self-engagement of the clutch doesn't happen. The engagement of the clutch should happen only when the spring is providing that force. Automatically, the engagement of the clutch should not happen. So to avoid self-engagement, the limit for angle alpha has to be greater than 11 or 12 degrees if your coefficient of friction value is around 0.2. So your alpha angle should be greater than tan inverse mu value. So if your mu value is equal to say 0.2, so tan inverse of 0.2 may come around 11 to 12 degrees. So normally the alpha angle for cone clutch is in the range from 10 degree to around 25 degree, depending upon the coefficient of friction. If the coefficient of friction is high, then again angle alpha can be increased. If coefficient of friction is small, then your angle alpha can be small. So to avoid self-engagement, you need to check out what is the coefficient of friction, and accordingly you can select the angle alpha. So normally the normal range of angle alpha is between 10 to 25 degrees. So you can, if you select between 10 to 25, then it will not create any much problem of self-engagement. So please keep in mind this angle alpha is very important, that semicone angle alpha. If this angle is too large, then what will be happening? Then your plate surface means this cone clutch will appear like a single plate clutch. So if your angle alpha is small, then it will appear as a cone clutch, and it will have advantage of smaller angle, as a smaller angle will give more torque transmission, and you can make your design compact. Okay, let's go for the next characteristic here. So again, cone clutch analysis for maximum torque. Since this is like a say similar like your single plate clutch, only the instead of say vertical surface, it has a inclined surface. Or say, and here also you will get similar relation, di and do relation. Y maybe you may be getting this y fraction around 0.577 only. So there is no much. So I will not waste the time on this. This you already learned. So only change from the perspective of cone clutch. So these two slides I can keep here. You can read it yourself. This is also similar. So I will not repeat. You already seen in the previous session here. Let's go to the problem statement. One of the problem statement. Understand how the cone clutch can be designed, because this design is not available in the PhD data. Problem here I am taking. A cone clutch is required to transmit 11 kilowatt at 960 RPM. Design following components by selecting suitable material and design spaces. One, you have to design the cone. Second, you have to design the cup. Third, you have to design the spring. Now, this spring design I'm not going to cover, because this is a part of your machine design one. So you can design yourself. Once you calculate axial force requirement, you can design the spring for yourself. Then driven shaft diameter. So draw neat sketches if required, of the components, indicate dimensions, assuming the time for each engagement. This is the additional data given. Assuming the time for the each engagement is around 0.125 seconds, and 30 engagements take place per hour. So this clutch is being engaged 30 times for a duration of 0.125 seconds for each engagement. Determine the steady state temperature of the outer surface. This part I am going to see in the next class. Determining the temperature heat transfer analysis we will see in the next class. At this moment we are covering the design part. Let's complete the geometric design part we are covering in this lecture. Thermal analysis we will see in the next class, because for that you need a better understanding. So determining steady state temperature and latter part of this problem we will see in the next class. So let's understand today how you can design this cone clutch for geometry. Okay, so as per our I am following the methodology what we are used for single plate or multi plate clutch. Same methodology we will try to follow, and we will pick up some data from the multi-plate clutch PhD data. Okay, so in given problem we have power given here as 11 kilowatt. So this value is 11. Then speed given here is 960 rpm. So speed of the shaft is 960 rpm. Then rated torque. So this formula is given in PhD 7.89. So this already I have demonstrated 2 to 3 times. So this formula is 97400 power in kilowatt upon speed in rpm here. So by putting these values in this formula, we get the rated torque here 1116.04 kg centimeter. Then again from the PhD data book 7.89, we get the formula for design torque for multi-plate clutch. Same formula can be used for this cone clutch also. MT is equal to KW into MT. So this KW is based on the driver driven operation and wear factor. So K1 is your driver factor. So we are considering electric motor directly connected to the mains. So K1 was 0.5. So this is available on PhD 7.90. So this also you have seen there. So I'm not going to repeat that. So we are taking that 0.5. Then K2 value we are considering dynamic characteristics with say medium duty machinery with variable torque requirement. So you can take K2L as 1.6. So we have taken the middle value. There is 1.25 value also and 2.5 value also. So we have taken the medium duty operation. So K2LA is equal to 1.6. So this is available on table in the table on page number 7.91. Then wear factor. Wear factor you have to calculate it for 960 rpm because the K3 value is available either for 620 rpm or 1000 rpm. So it is not available in the table for 960 rpm. So you have to do the linear interpolation. Again, these values are available on the PhD 7.91. So from the 7.91 pages, we have taken the value of K3 at 620 and 1000 rpm. So these values are 0.25 and 0.32 respectively. So by putting these values, we get wear factor K3 at 960 rpm is equal to 0.3126. Then you have to calculate K4 operation frequency factor. For operation frequency factor, we have assumed number of operations or number of engagement, disengagement there in earlier problem. But in this problem, you can see, assuming the time of each engagement is equal to 0.125 seconds, and there are 30 engagement takes place per hour. So already this data is given in the problem. So how many engagements are taking place? So 30. So 30 engagements are happening in how much time? Say 1 hour. But this K4 is based on 8 hours duty. So engagement for 8 hour shift. So if I consider 8 hour shift, then the number of engagements in 8 hour shift will be engagement per hour, that is 30 into number of hours. Number of hours are here 8. So 30 into 8 is equal to 240 times. So number of engagements we require in a day of in a shift of 8 hours is 240. Now you can determine K4 value for 240. So from PhD data book, there is a direct value available for 240 operations, frequency operations. So frequency factor here K4 is equal to 1.8, which is taken from 7.91. I will show because this is very critical. Take K4 factor here, frequency factor here. Number of engagements in 8 hour shift. So we have number of engagement in 8 hour shift are 240. So your K4 factor here, K4 factor or frequency factor here is 1.8. So this value you are taking in the design calculation. So we are taking this value in the design calculation here. Now you got all the values of K1, K2, K3, K4. Then you can calculate here KW. So addition of summation of all these factors here, that comes out to be 4.2126 by adding all these factors here. Therefore, design torque will be MT is equal to KW into MT, small MT. So this value comes out to be 4701.46. So this is your design torque. So you are going to design now cone clutch for this design torque value of 4701.46. So step number 1 we have completed. So we have calculated the rated torque and design torque. So let's go to the next step. That is we need to know what should be the shaft diameter. This is a driven shaft diameter. So driven shaft diameter, this formula is available on page number 7.89. Square root of 49500 kilowatts into kW upon speed up into design shear stress value. So you can check this formula. I will show this formula. So you can check this formula available on 7.89 here. Shaft diameter. This is the diameter of the clutch shaft. D is equal to cube root of 49500 into power in kilowatt into kW upon speed upon design torque. So this value, allowable shear stress value. So if you consider the material is a steel material, and if you consider commercial shafting. So in commercial shafting, the shaft with keyways, the permissible shear stress value is around 45 Newton per millimeter square, and without keyway it is 55 Newton per millimeter square. So we are taking that 45 Newton per millimeter square to determine the minimum clutch diameter, minimum shaft diameter here. So let's go to the design calculation by taking this formula and the value here. Okay, so I'm just magnifying that. Now in this formula we are putting the known value. We know the power here, which is 11 kilowatts. Then we have calculated right now kW, that is 4.2126. We know the speed. The speed here is 960 rpm. Now tau value we are putting for the commercial steel shafting. For commercial steel shafting with keyway or spline shaft, this tau value is equal to 45 Newton per millimeter square. Now in this formula we have to put this in terms of kJ per centimeter square. So this value in kJ per centimeter is equal to 450 kJ per centimeter square. So by putting this value as 450 kJ per centimeter square, so we get the diameter here. Diameter required for the shaft as 3.75 centimeter. So which is equal to 37.5 millimeter. So we can approximate this is equal to 4 centimeter. So we can take the diameter of the shaft as 40 mm. So we have evaluated one geometry required in the cone clutch, that is the shaft diameter. Now let's go to the another geometry calculation. Internal oblique small end diameter of the cone, which can be assumed or which can be calculated. So I have shown here calculated value. Let's take with some assumption. So we are considering uniform wear theory, and cone and cup is made up of same material. Say let's say cone material and cup material is a steel material here. You can have cone and cup made up of cast iron material also, depending upon the requirement. If the size is big, they are normally made up of cast iron material. If the size is small, then they are made up of steel material. So let's say they are made up of steel material. So cone smaller diameter D2 is equal to, has to be at least 1.5 times the your shaft diameter, because it has to be housed on the shaft with a hub. So hub should have minimum thickness. So to maintain that minimum thickness, we are taking D2 is equal to 1.5 D. So if we put the value of D here as 40 mm, so we get D2 is equal to 60 mm, that is equal to 6 cm. So this is the internal diameter or small end diameter of the cone, which is equal to D2, that is equal to 6 cm. Now we have to check whether at this point we are selected that hub thickness with hub diameter as 6 cm, whether that hub is safe in particular spaces or not. So normally hub is checked for torsional shear stress. So checking for torsional shear stresses in the hub. The formula for torsional shear stress, this is the shear stress induced in the hub, is equal to 60 into the design torque upon pi d2. D2 is the hub diameter here, pi d2 cube into 1 minus d upon d2 raised to 4. So d is the shaft diameter and d2 is your hub diameter. So hub here it is considered as a hollow shaft, and this is the formula for shear stress induced for hollow shaft. So we are using the concept of hollow shaft. You have to remember this formula. This is not given in the PhD data book. You have to remember this formula. So you can check out how much is the shear stress induced in the hub section. So if you put the value of MT, that is the design torque, then D2 we have taken by proportion as 6 centimeters, so 6 centimeters here. Then D is equal to 4 centimeters, and if you do this calculation, you get the tau value in terms of kJ per centimeter square. So this value is 138.14 kJ per centimeter square. Now for steel material, permissible value of tau is in the range from 300 to 450. Right now we have done the value calculation with 450 tau value. So this value is permitted in the range of 300 to 450 or less than that. So even though it is considered lower side also, this value is less than this lower value. So your hub is safe in torsional shear failure. So it means your hub is safe here. So there is no problem with hub. Now, so hub diameter is safe. Say D2 is safe. Now we have to go for bigger end diameter. So step 3, one geometry you have calculated. Now we can go for step 4, that is external or big end diameter of cone. Now this is done by calculation. So for that we have to use a lot of data here. So we are considering here steel plates in dry condition. We are not considering that we are using lubricating there. So let's say we are not using lubricating. So let's say consider these plates are in dry condition. So the bearing pressure, maximum bearing pressure when it is dry condition, that is equal to 2.5 into 3 kJ per centimeter square. This value is taken from the PhD, from the multiplate plus data. So I'm showing that data where it is taken. This is from page number 7.89. Okay. So this value here, allowable pressure, we are determining the what is should be the PA allowed, because this is not given in the problem. In earlier problem, we have seen this PA was directly given. So we have to calculate this PA from PB. So PB for steel plates. So steel plates, wet running condition, steel plates, dry condition, compressed asbestos material on steel, then these values are there. So for steel plates, dry running condition I am considering, the value is between 2.5 to 3 kJ per centimeter square. So this PB value here is equal to 2.5 into 3 kJ. Then we require K here to get the value of PA. This K value is available from a chart here. The available from chart here. So the chart is available on page number 7.90 here. So this K value chart is here. So this K value depends upon your velocity at maximum radius. At this moment, we don't know the maximum radius D1. So you cannot calculate velocity. So for understanding purpose, you can take the velocity in the range around 10 or between 8 to 10 meter per second. So if you take say 10 meter per second velocity, peripheral velocity of your cone clutch at maximum end diameter, then you can get this K value in the range of around 0.6. So I am taking this K value around 0.6, and then from that we can calculate allowable bearing pressure PA, or allowable pressure between the plate here, cone plate and clutch plate, cup plate here, cup surface here. So we can calculate PA is equal to K into PV. Sorry. So we are calculating now allowable pressure here. Allowable pressure by this formula, PA is equal to K into PB, and PB is in the range from 2.5 to 3. So let's say lower, I'm taking lower value of 2.5. So 0.6 into 2.5. So allowable pressure here is 1.5 kJ per centimeter square. Now from this allowable pressure, you can calculate axial force engagement. Now this, since we are using uniform wear theory, using the formula for axial force engagement, uniform pressure theory formula, so which is equal to pi into P2 into D2 upon 2 into D1 minus 2. Now P2 is the maximum pressure permissible as per uniform wear theory, which is equal to now allowable pressure PA, that is equal to 1.5. So we can put the value of P2, D2, D1 will be unknown, so we will get W in terms of D1. So we are calculating W here, axial force requirement here, pi into P2 is 1.5, D2 is calculated right now, that is 6 centimeter, that is 6. into D1 unknown, so D1 minus 6. So after simplifying this equation, we get axial load here, axial force here requirement is equal to 14.13 into D1 minus 6 kgf. Now we have a torque transmitted formula for uniform wear theory. So for uniform wear theory, torque transmitted design torque will be equal to mu W upon 4 sin alpha into D1 plus 2. Now, in this formula, we can put this W value from above relation, this relation, that is 14.13 into D1 minus 3. So, let's say, again, you have to put alpha, consider alpha here. Right now, I have discussed regarding alpha. Your range of alpha should be between 10 to 25 degree, when your mu value is in the range from 0.2 to 0.35. So, since I am considering mu value here as 0.3 being dry friction, whenever there is a dry friction, or if you consider surfaces are dry, then your coefficient of friction can be in the range from 0.2 to 0.35. If your surfaces are wet or wet friction you consider, then this value is lower. So this value maybe come down to say 0.05 to 0.15 for wet friction. So considering dry friction, we are taking mu is equal to 0.3, and considering that mu around 0.3, let's take alpha is equal to 50. And now let's put in this value as well as put the value of W, and as well as put the value of design torque here. So by putting the design torque value of 4701.46, mu value is equal to 0.3. Then W from this formula, that is 14.13 into D1 minus 6 upon 4 sin alpha, 4 into sin 15, plus D1 plus D2. D1 is unknown, so D1 as it is plus 6. So we can multiply this factor. So this comes as D1 square minus 36. So D1 square minus 36, and remaining terms reordered, we get this formula, this value as 1148.22. Now from this you can determine D1. So D1 we get as 10.57 centimeters, which is equal to 105.7 centimeters. So that is approximately equal to 110 millimeters. So you can take the outer end of your cone diameter is equal to 110 millimeters. So we have evaluated shaft diameter, we have evaluated internal cone diameter, we have evaluated now outer cone diameter. Now the cone will have thickness, the cone and cup has thickness. So we have evaluated cone and cup dimensions right now, that thickness. Now you have to evaluate thickness. So next step, you are evaluating the thickness of that cone. We are evaluating your thickness of the cone as well as length of the contact surface. So thickness of the cone we are evaluating in the next step. So for that you have to consider again shear failure. So let's how this formula is applied. Let's go to the diagram, then you can understand. So I am going to the diagram here, so you can understand that. So I will show the cone diagram, detailed diagram here. You can see here, I am assuming this surface is here. My cone is starting here. So if my cone is starting here at this point, so at this point there is a minimum thickness available. There is a minimum thickness available. So there is a chances this thickness is continued here. This thickness is continued here. So there is a chances this plate may fail under this thickness here. So what type of failure is happening here? So since these parts are rotating, the failure is available here is that again torsional shear failure. So the failure available here is the lateral surface area. The lateral surface area available here is pi into this diameter. Say this diameter is equal to half diameter is equal to say D2. So pi D2 into the thickness. So thickness of this plate I am assuming as T. So considering that thickness, you can calculate that minimum required thickness by considering the shear failure. So if we go to the final design calculation here, the considering shear failure at the hub point where your cup or cone starts. So we are considering the design torque or rated torque to be transmitted, design shear stress value into pi. This I am considering this cone itself starting at the half diameter, so D2 into thickness T. So we have this value as 4701.46. So I have written 4701 into this value, tau value for the material. It is range from 300 to 450 design value. So I am taking design value of 300 kg per centimeter square. Then I am putting the value of D2, which is 6 centimeter, and thickness in centimeter we can calculate here. So after doing this calculation, you get the thickness here. The thickness here as 0.83 centimeter, that is equal to 8.3 millimeter. So you can approximately take the thickness of your cone or thickness of your cup as 10 millimeter. So you can take the thickness of cup and cone as 10 millimeter. Then you have to calculate length of contact surface. So length of the contact surface, this formula already I explained, that B is equal to D1 minus D2 upon 2 sin alpha. So D1 is 11 centimeter because 110 millimeter means 11 centimeter. D2 is 6 centimeters. Alpha is 15. So by putting this value, you get the face width of your cone. So face width of the cone should be approximately 9.65 centimeters. That is 96.5 millimeter. So you can take approximate minimum value as 100 millimeters. So you can have face width of your cone or length of your cone, that is a lateral length, inclined length of your cone can be 100 mm. Okay, so this is the cup thickness, cup or cone thickness, as well as drum length or cone length. Your cup drum length or cone drum length is equal to 100 mm. Now this cone will be engaged with a cup with the help of a spring force. So you can calculate now spring force. So spring force requirement as per the uniform wear theory, axial force for engagement for uniform wear theory, W is equal to pi into P2 into D2 upon 2 into D1 minus D2. So this was, we have calculated in this form, that as 14.13 into D1 minus 6. So D1 has come as, we have taken as 11. So 14.13 into 11 minus 6. So this comes as to be 17.65 kgf. And you have to design a spring, or you have to select a spring so that it produces a spring force for engagement equal to 70.65 kgf. Disengagement force will be greater than this force. So when you operate a lever for disengagement, you have to apply a force greater than 70.65 kgf. Then only the disengagement of cone clutch will happen. Otherwise, the cone clutch will be remain engaged under the spring force. Now to determine the spring size, you can start, you know the half diameter. So half diameter is 6 centimeters. So you can consider your spring is mounted on hub, or you can say your spring is mounted on your say shaft. So you know shaft diameter is 4 centimeters. So you can take inside diameter as 4 centimeters, and this much force has to be developed. You can design a helical spring. So that is covered in machine design 1. So you can use that approach for designing of machine design, and you can take the KS factor. You can check and you can find out the what should be the free length of the helical spring, what is the compressed length, and how many number of turns will be required, what should be the wire size, what should be the mean coil diameter. That you can do it in the calculation. But in exam point of view, this is not required. What is required is up to this. You have to calculate spring force, and you can say the spring can be selected or designed for the required spring force strength. Okay, so in this problem now what is left out is only the thermal analysis of the cone clutch. So that we will see in the next class, thermal analysis, and we will see centrifugal clutch design in the next class. So we will stop here. So if you have any doubt regarding cone clutch working, cone clutch analysis, and cone clutch problem solving, so you can ask the doubt. So you can unmute and ask the doubt, or you can put in the chat box.